So last time we learned how to represent a matrix in such a way that it makes easy the computation of h of v. So we have, represent a map so that it makes easy the computation of h of v. So we basically put the information that we need into a matrix. We just take these columns and put them one next to each other, and then we figured out the way that the numbers in that kind of tiny little database, the way that the numbers in that matrix combine with the numbers for the representation of the vector, and it just turns out to be this sort of these things combined with these things. We call that the definition of matrix vector multiplication, and that's how we compute the effect of a linear map. If we have an arbitrary linear map, that's how we figure out how to compute it. So of course, the check-in exactly asks us to to do an example of that. Of course it does. So let's have a whack. Okay, so let's see now. Whoops, push my stuff out of the way. Let's have a look. So looking at here a map that took, darn it, all this stuff is all over the place. There we go. We have a map that takes the plane to the 2x2 matrices. And it's given by, oops, I didn't make my R line very good. It's given by xy goes to 3x, 0, 0, and 2x minus y. I don't know, I made it a 2x2 matrix, and I didn't want to have too much in there just to make it, it just simply makes it longer to do. It doesn't illustrate anymore, so I made it a diagonal matrix. Okay, and of course the first question said represent it with respect to the bases, so I have to write down the bases if I can get them right. B is Hadamard basis 1, 1, 1 minus 1. And D is a basis for the 2x2 matrices that is supposed to be not trivial. I've mentioned any number of times that when you're making up examples for yourself to think about, you don't want to make up sort of the easiest possible example, but you don't want to be too hard either. So I is 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, and 0, 0, 0, 4. Okay, so just a tip, you don't want it to be too hard, but you don't want it to be too easy. Too easy can hide some subtleties. Too hard is just, you're just beating yourself up. Okay, so let's represent this map here, H, with respect to these bases. So the steps are, first of all, figure out what does H do to each basis element. So H does to 1, 1, and H does to 1 minus 1. And now just go up here. What H does to 1, 1 is it sends it to 3, 0, 0, 1. 2 times 1 minus 1 is 1. And what does H do to 1 minus 1? Why, it sends it to 3, 0, 0, 3. Okay. Represent that with respect to D. So the representation with respect to D of the first thing, 3, 0, 0, 1, and the representation with respect to D of the second thing, 3, 0, 0, 3. Okay, and again, I didn't make D too hard because I don't want to have to go through the Gauss's method where I won't learn anything new, but I didn't want to make it too easy. So anyway, I made what I made it. So how many of these, how many of these, how many of these, and how many of these do you need? So I guess it seems to me you need 3 of these, 0 of these, 0 of these, and 1/4 of these. I'll put down a little d there just to emphasize. Okay, and likewise down here, I didn't really make enough room. 3, 0, 0, 3/4. D, that's a 3/4. I'm sorry, my handwriting is so embarrassing. 3, 0, 0, 3/4. So for a person who can't read, 3/4 it says. Okay, and then to represent the matrix with respect to the bases, to represent the map with respect to the bases, representation with respect to B comma D of the map H, you just take these two and put them into a matrix. 3, 0, 0, 1/4, 3, 0, 0, 3/4. We often leave the subscript out, but since I'm illustrating, I'll put it in the subscript. 2 is to represent the vector. I think the vector was 5, 3. So we want to represent, with respect to b, the vector v equals 5, 3. So if you remember the basis up here, so I'm looking to write down something like a times 1, 1 plus b times 1 minus 1 equals 5, 3. And of course that gives you some linear system. You're looking at a plus b equals 5 and a minus b equals 3. And I'll show you a tip about this basis up here. I'll show you a little trick. I mean, you know, nobody made it a crime to know something. Of course, I could go ahead with Gauss's method and get an answer, and I've done that a half dozen times with this basis already. But maybe we're at the point now where we're ready to be able to look at things and say, aha, this is an old friend. I know just what to do. Okay, so this particular basis is an old friend, and the way to look at this linear system is you say to yourself something, well, that from A, if I go up, I get to 5. If I go down, I get to 3. So that is to say, A is right smack in the middle. A is the average of the two. A is 5 plus 3 over 2. I know that's 4. And B is the increment. B is the amount you go up or down. So from 4, you go up to get to 5. From 4, you go down to get to 3. So B is the increment. You could write down increment. Nobody made that a crime, but I'll write it as 5 minus 3 over 2. In short, the representation with respect to B of 5, 3 is what to 4, 1. And again, I'm illustrating what's happening, so trying to be extra careful about writing the parts. Okay, and then there's a part 3 that I don't think I left myself enough room for on this piece of paper. So let me do the part 3. Part 3. I want to use those two, the matrix and the representation of the vector. So the representation of the map and the representation of the vector, I want to use those two to figure out what is h of v. What is the representation with respect to d of h of v? Okay, and the answer is a question of writing down the matrix. See if I copy the matrix from what I had. It was 3, 3, 0, 0, 0, 0, and 1/4, 3/4. The representation of the vector was a 4, 1. I just wrote it a second ago. You'd think I could remember it, but. And the answer is going to be a representation with respect to d. I'll compute it, but the answer is going to be a representation with respect to d. Okay, and we saw that the parts just combine in whatever way they combine. We call that combination the dot product, but in any event, the parts just combine. That's just the way that the combinatorics works out. So 3 times 4 plus 3 times 1 makes 15. 0, 0, and 1/4 times 4 plus 3/4 times 1 makes 7/4. So this is the representation with respect to d of the answer. To make it concrete, of course, I'm going to check. That's right. It's always wise to check, so I'm going to check. So the definition of h says that 5, 3 under h goes to, let's see, this said 3x, so that's going to be 15. Then 0 and 0, and this said, 2x minus y, so 2 times 5 is 10, minus 3 is 7. And what's the representation? Representation with respect to d of 15, 0, 0, 7. So how many times 1, 0, 0, 0? How many times 0, 2, 0, 0? How many times 0, 0, 3, 0? And how many times 0, 0, 0, 4? So yeah, that's right. Okay, very good. Okay, so this is a key result. We are figuring out how to work with arbitrary arbitrary maps, not to sort of rotation, nothing wrong with rotation or projection or dilation, but we're trying to work with arbitrary, any old kind of maps, and so we're representing those using a computational scheme that is going to enable us to do arbitrary computations. If you're in science or engineering sort of stuff, you're trying to model fluid flow over an airplane wing or so, well, you don't expect your matrices to have lots of zeros in them or sort of stuff. You expect it to be kind of a mess. So here's the theorem that we just practiced with. If you have the representation of the map and the representation of the vector, then the combinatorics, the way that the parts put themselves together is you take the row here and combine it with the column there using the dot product operation, and you get that first entry. You take the second row, combine it with the single column, you get the second entry. You finally down to the mth row, combine it with the single column, and you get the mth entry. Okay, so this is the theorem that we just applied to do the check-in. So just skip past here. We defined the matrix vector product to be that operation. This is the natural way to combine matrices and vectors. It's natural because it turns out to be what you want to do. When you want to represent how this arbitrary sort of function, linear function, is working, why you want to write down its representation and the representation of the input vector, and then that's how the parts get put together. Now, last time we stopped with the definition of matrix vector product, but I want to go on and explore it just a little more today. First point. We can perform the matrix vector product operation, but without any talk about maps or spaces or bases. You absolutely can write down a kind of an arbitrary matrix and an arbitrary vector and combine them in the way that's defined in the definition there in the line above. And it so happens when you write down this matrix and this vector, you get 5 minus 13 for the components of the result, I hope. and it's just simply a sort of mechanical process. And there's in the exercises, there's lots of examples of there's at least a couple of examples of that this turns out to be handy even in contexts where you don't immediately say we're looking at a linear map. I mean, you can have data about how many, what is the pay per hour of the employees and how many hours did they work, and when you combine them, you get what should be the total pay of the employees, kind of stuff. So matrix vector product, we defined it because in the representation of the action of a linear map, it's how the representation of the map and the representation of the input vector combine to give a representation of the output vector, but you can use this definition in other ways. In particular, the product of this matrix and this vector is not defined because you have the wrong sizes. Up here, it's careful to say an m by n matrix, and an n by 1 column vector. So that n and that n have to be the same. So that's in the definition. It's careful to say the n and the n have to be the same. But just looking down here, if you tried to take the first row 1, 2 and combine it with the 5, 6, 7, you'd take 1 times 5, 2 times 6, and you got nothing to go with the 7. Are you going to make up a 0 or a 1? That doesn't make any sense. You simply instead say not defined. In practice, when one of these is not defined, it's typically telling you you've made a mistake. You've tried to put together parts that don't make any sense. There's some analogy to when you're doing computer programming and you're trying to combine two objects of different types. If you take, for example, a string and you try to combine it somehow with a matrix, and you say, well, strings and matrices don't combine via addition, that's because you programmed something wrong. So too here, in some sense, the type of this is 2 by 2. The type of this is 3 by 1, and the two types just don't mesh. So in practice, usually when you see something like that, it's a caution that you've done something wrong. You should back up and figure out which part you're putting and which part that doesn't fit. Okay, and I just want to do 2 examples because this idea of representing the map by some systematic process, representing the map and then using it to figure out where the vectors go is a key idea that we're going to spend really the rest of the semester on. Okay, so the familiar geometric action of projection here onto the x-axis, we saw this before, that if you fix these bases and you want to represent projection onto the x-axis, you do it with this matrix. I'm going to pick a particular domain vector, and I picked minus 1, 5. And again, you know my scheme for picking things to make examples. I try to pick things that are not too hard, but also not too easy. So minus numbers, plus numbers, not 5,000, just 5, but not 1, 0 either. Okay, and so now I have to represent V with respect to the domain basis. That's the domain basis. It looks a lot like the one we did on the check-in. Anyway, you represent minus 1, 5 with respect to the domain basis, and it turns out to be a 2 and a 3, a 2 and a 3. And then you just combine to get minus 1 times 2, 1 times 3 gives you the 1. 1 half times 2 minus 1 half times 3 gives you the minus 1 half. And this is the representation with respect to the output basis, with respect to the codomain basis. This is the representation with respect to the codomain basis of the result of projecting minus 1, 5 down onto the x-axis. So, of course, I'm going to check. Of course I am. If you project minus 1, 5 down onto the x-axis, you should get minus 1, 0. So does minus 1, 0 work out to be what happens if you take the 1 and the minus 1? And it does. Of course it does. Of course, I would have changed the slide to make it right. Okay, so just like the check-in. So can't overemphasize that. I know often people coming to this class have seen matrix vector multiplication before. That's great. It's good to know things. That's absolutely fine. But I'm presenting a point of view, and the point of view is that the functions come first. The central object of study here is the functions. The matrices represent those functions. So I'll make some analogy. It's a silly analogy, but it helps me. So one time I took a trip to go go visit a conference, faraway conference, and I drove there. I had when I went through tolls, I had receipts from the tolls. I had meal receipts. I had a receipt for the hotel, all that kind of stuff. I brought it back and I handed it in to the person in the accounting office. Okay. To me, what happened was a trip. That the accounting, the sort of numbers, the receipts, all that stuff was what was sort of representing my trip, was kind of what you use to compute my trip, but it isn't actually the trip. So too here, the point of view that we're taking is that the functions, the linear functions, the h's and g's, the functions are the real thing, and the matrices only represent those functions. That doesn't mean that they're embarrassing, but it means that the real things are the functions. The pi is the real thing, and the matrix vector multiplication, which you may have learned in another class, is the way in which we compute the function. Okay, so we're giving the function primary, trying to help a person build the right mental scaffolding in their mind. What comes first, what comes second? And the point of view that we're presenting is that what comes first is functions of a certain kind, linear functions, homomorphisms, and what comes second is that the matrices and column vectors represent those in the way that the receipts, the chits that I handed in, represented my trip. They're not actually the trip. Okay, enough of a lecture of finger wagging. One more example. So here's a map that we saw before, so I don't have to compute the matrix representation kind of stuff. So this map sends R2 to R, and it sends the too tall vector AB over to the single number 2A plus 3B. So that's right. And I represented it with respect to the standard bases E2 and E1 by 2, 3. Okay, not a coincidence that it's 2 and 3 because things are represented by themselves with respect to standard basis. But anyway, you'll remember from a prior slide we saw that. If I take a domain basis, domain vector, for example, minus 2, 2, represented with respect to the standard basis, of course it represents itself. That's the good thing. That's the easy thing about the standard basis. And then if I want to figure out what is h of v, what does h do to negative 2, positive 2, when A is negative 2 and B is positive 2. Y, you take 2, 3, that's a 1 row, 2 column matrix. You multiply it by this column vector, minus 2, 2, and you get here 4, take away, negative 4, add 6, and you get just the 1 row, 1 column matrix. Sometimes people leave out the matrix, the parentheses. 1 row, 1 column, 2. And of course, since that's a representation with respect to the standard basis E1, in fact, the image is H of V is 2. Okay? Okay, so next time we're going to reverse what we have here. We've figured out how to represent a linear map with respect to bases by using a matrix, and now we want to work with arbitrary linear maps. So what we need to do next is we need to show that whatever matrix you write down is a linear map, and so that's what we'll do next time. Okay, very good.